The broadcast is now starting. All attendees are in listen-only mode.
Welcome to WESTPAK's webinar entitled The Shocking Truth About the Frequency Domain. Hello, my name is Edmund Tang, and I will be your moderator and webinar organizer today. Before we start, let's take a moment to ensure that everyone is ready and familiar with the webinar control panel. First, you should have a control panel on the right side of your screen. You can minimize the panel by clicking on the orange arrow in the upper left-hand corner. You may expand the panel by clicking the same button again. Secondly, you have the ability to submit questions using the chat pane located near the bottom of the control panel. We will be answering a few questions during the webinar. However, if we are unable to address your questions during the webinar, one of our presenters will follow up with you with an email afterwards. Today's webinar's video should be available on WESTPAK's website by Friday. For those of you who are logged in to the live webinar, you can download a copy of the slide deck now. You can find it in the chat pane window in the handout section, located just above the questions area. With that, let's get started. Herb, you plan to tell us a bit about yourself and how you got to WESTPAK, so please take it away.
Okay, thank you, Edmund, and welcome all to our ongoing webinar series. As Edmund said, we're going to be talking about the frequency domain today and why it's important and to make you all frequency domain experts, I hope. A little bit of background, I'm fully retired from WESTPAK now, and it was interesting for me to kind of follow my career in terms of a bio, in terms of the 10-year or decade segments. And here's kind of the what I came away from that. I graduated from high school in the mid-60s and college in the early 70s, and then started my professional career. Saw a lot of growth, and let's call it professional growth, and there pain and peaks and the whole thing. And then started in the early 2000s series, passing the torch on, if you will, and that process is completed. And my overwhelming feeling following that is this what I call amazing grace, which is my method of saying it's been a great ride, folks. It really has. I'm not going to fade away instantly, but slowly, perhaps. Here's a more traditional bio. I actually, like Edmund said, I'm chairman of the board of WESTPAK. I've been president and CEO since the founding, which we launched in 1986. And previously, I'd worked for the Western Electric Company in the Chicago area for Baxter Travenol, as it was called in those days, laboratory for the Clorox Company, and then for Lansmont. Many of you know Lansmont. I have a bachelor's degree from Michigan State University and an MBA from Northern Illinois University. And for those who are interested in raising things, I was raised on a farm and still enjoy the gardening aspect. What we're going to be doing today is all about dynamics, but you have to understand the lingo in order to understand dynamics, or almost anything for that matter. But let's concentrate a little bit on the dynamics and the lingo thereof. Dynamics is a study of motions of bodies. In other words, it's distinguished from statics. So dynamics means things are moving. First of all, we're going to talk about the time domain and how we collect data and series of data in the time domain. So it's with respect to real time rather than frequency. And then we're going to talk about the inverse of that, which is the frequency domain, 1 over time, and why we do it, why it's helpful, why we would even consider that, and go on from there. So the scope includes both the dynamics, time domain, frequency domain, and we're going to spend a lot of time on case studies, which I consider to be pretty important and probably are as good a learning tool as anything. So let's start here. Some people ask, does shock come first or vibration? And what I'm trying to say here is that shock is actually a subset of vibration. So it is, in fact, the other way around. In other words, we analyze shock in terms of a single half cycle of vibration rather than the other way around. So vibration is the start of our analysis rather than shock. We're going to talk about random vibration, and it can be easily described, I think, as a series of polarized excursions, in other words, plus and minus excursions from a reference point, a 0 point, if you will, and that these excursions vary randomly in amplitude on the x-axis and frequency on the horizontal axis over some period of time. So that's probably as good a definition of random vibration as we can come up with. And random is by far the most widely used tool, and the reason is it duplicates the real environment much better. We started off our vibration work, if you will, several decades ago, as I indicated earlier, using sine vibration. And the reason that we use sine is that we had a very difficult time doing random, and sine was much easier. And sinusoidal vibration is that vibration where the amplitude normally doesn't vary. It's fairly constant, and the frequency it varies, but in control of the operator. Okay, so sinusoidal vibration is definitely a much more operator-controlled function than random vibration. And we're going to get into this a little bit later in depth, but I want you to at least understand that there is a difference between sine and random vibration, and that of the two, sinusoidal vibration has much more to do with the operator than random. Here's a kind of a graphical representation of sinusoidal vibration. We see in this first article, this little ditty here, that sine vibration starts at a 0 amplitude, reaches some positive peak, goes past the 0 point to some negative peak, and then back to 0 as a function of time right here. Okay, so we have amplitude versus time, and we call that the time domain. Interesting. As opposed to the frequency domain, where you have again, some amplitude. It may not be the same as the time domain, but it's an amplitude nonetheless, as a function of frequency. So frequency starts low and heads to high, and this same sinusoidal function seen above is represented by a line at a certain frequency. And the reason is that this sinusoidal vibration will give you one particular frequency, so that's right there, and has some given amplitude right there. So the sinusoidal function that we see above is represented here below as a straight line, if you will, indicating amplitude at a given frequency, and that we call the frequency domain. I'm sure you're asking, what the heck is the difference here, and why am I important, or why should I even study this? But we'll get to that in a minute. What we can say is that the frequency domain is really, F sub n is the reciprocal of the time domain, and 1 over the period of the time domain. So the period is the time necessary for sinusoidal vibration to complete one cycle, and the frequency domain is simply the inverse of that. So where does this sine vibration come from? As I mentioned, it was the first thing on the menu. And basically, if you take a spring mass system, so you have some mass suspended by some spring in this particular case, and you start that oscillating, so you deflect the mass and you start it oscillating, and then you simply put a pen, if you will, on the side of that mass and record the motion of that mass as the pen scribes on some moving paper alongside of it. Guess what? You wind up with a sinusoid, just like this. So that's where it comes from. And again, it's amplitude, the vertical axis versus time on the horizontal axis. As opposed to random vibration, which we see here in the time domain on the top. So we see this motion that varies randomly in amplitude with time. So both the frequency and the amplitude vary randomly with respect to time. But again, it's amplitude versus time on that display. As opposed to the frequency domain, or the reciprocal of that, here we have amplitude on the vertical axis, and again, frequency on the horizontal axis. And what this represents is that at some low frequency, the amplitude is fairly low. So if we look up here and find something that's low frequency with low amplitude, we might say, oh, there it is right there. Okay, or it might be something similar. As we increase the frequency, we see that the amplitude increases. Okay, so amplitude increases and frequency increases. And if we see a higher frequency is going to be a shorter duration, so it's going to be one of these shorter peaks, if you will, but they could be fairly high. And what this says is on average, these peaks reach this particular amplitude level, and that's about what we see here as well. And then following some higher frequency cutoff, the amplitude decreases. So at very high frequencies, we're going to see lower amplitude, and you might see that in areas such as this, or these very small peaks here, things like that. So we see that this frequency domain is actually a much easier representation of this time domain, okay? Because it would be very difficult to get all of these highs and lows and peaks into our analysis. But if we simply use the frequency domain, there it is. So that's the primary reason why we use the frequency domain. It doesn't occur in real life, but it's very handy when we talk about the laboratory data. So in summary, a spectrum, which is the picture that I just showed you, can be described as a frequency domain representation of a time domain event. Okay, relatively simple. In fact, Edmund will likely recall that I used to kind of pound this into the students in the beginning class in packaging dynamics. So that's what we're looking at, a frequency domain representation of a time domain event. Very simple. To bring the point home, I want to emphasize that we live in the time domain. That's everything that we do essentially is in the time domain. So we age. I'm probably the classic example of that right now. I'm at least in this group. So, passage of time. Okay, years we call it. We travel in terms of our speed, our miles per hour. So again, time domain. Do X number of miles in Y number of hours. We normally earn our salary as a function of time. We get so many dollars per hour. And it's also used to describe shock events. So it's some amplitude versus time. So that's the time domain. So I hope that's fairly clear. In vibration, which is really what we're going to try to focus on in this particular webinar, we know that all this laboratory data is generated and controlled in the time domain. In other words, we get these kind of functions, as I showed earlier, this sinusoidal function. Okay, in other words, amplitude versus time. Okay, racers function race as a function of time, things like that. The problem is that we have to communicate with these vibration machines, the controllers, if you will, in ways that are not in the time domain. In other words, we can't tell it what each cycle it has to do is. We can give it kind of a bulk picture, if you will, and then we allow the machine to actually create the time domain signal, in this case, a random signal that we're looking for. This is a pretty good representation that I found that shows the amplitude versus time on one axis and the frequency domain on the other axis. In other words, if we were looking at this whole thing from the time domain axis, we would see these highs and lows. If we were looking at it strictly from the frequency domain axis, we'd simply see these amplitude lines that are shown here. Okay, and then as if we take all of this information and put it into what I earlier described as a spectrum, we would see something that looks like this, perhaps. Amplitude on the vertical axis, frequency on the horizontal axis. Okay, so that's where it all comes from. You've probably seen something like this if you've used laboratory vibration data or generate that data, but that's where it comes from. And I think it's important that we recognize that. That is a background. I'm asking a question here. How does this vibration controller that we're using to control our test convert this input spectrum, in other words, the amplitude versus frequency line, if we will, that we give it, which is a frequency domain thing, how does it convert that to the time domain signal, which it needs to control the machine? Okay, I often wondered that. I said, how in the world does this machine take this nice straight line and produce all these ups and down bumps, if you will, in response? And the answer is interesting, but it's also very informative in terms of the understanding the frequency domain, and therefore uh, this phenomenon of analyzing things in the frequency domain. So how does a machine do that? Well, for sine, certainly for digitally created sine, the vibration controller synthesizes it. Basically, it does a series of stair steps, if you will, up and down stair steps. And there has to be at least 8 of these stair steps or control points for each cycle of the vibration that's creating. Otherwise, it gets into aliasing and it's more difficult to control. Uh, Now, that's simply a product of the fact that we're trying to digitize it, and that works well if we're using computers. We didn't used to use computers for this. We used to use analog devices. So if we're trying to do a sine vibration using the old analog device, it was very simple. We simply get a function generator, something that made a noise, if you will, uh, and then we would simply vary the frequency and the amplitude to achieve this. So varying the frequency meant that the noise went from low to high frequency, and the amplitude went high to low as a function of the volume of the function generator. So it was easy to do. And when we converted to the digital world in the probably starting in the 1970s, became less easy to do. That's for so enough about that. Let's get on to our actual vibration data itself. And I really want to answer this question first because it's critical to the whole area of the frequency domain analysis, and that is we use the frequency domain to identify resonance. Okay, that's the whole purpose of this whole exercise is to say that's how we get the natural or resonant frequency of a responding system, whether that system is a product or a package or both. That's what we're looking for. And this is, or in my analysis, should be the primary reason for the vibration testing in the first place. So for the extra credits for the students that are interested, I said, why is this so? In other words, why is it necessary to determine resonance? And the answer is that resonance is where damage is going to occur. Okay, so any particular system that we're shipping is not likely to be damaged by vibration-induced excitation, except when resonances within the product or package are excited by vehicles, typically in the distribution environment. Okay, so the short answer is we're interested in resonance because that's where the money is, if you will, or the money isn't in case of damage. So uh, resonant frequency identification is critical because that's where damage occurs. As I mentioned earlier, we measure the response in the time domain, but we report and display it in the frequency domain. What does that mean? Well, basically, it means that even though we specify this vibration, mostly random vibration, in the time domain, we always use the information in the frequency domain. And the reason is quite simple. It's easier. It's just much easier. And let me explain why. Before I do that, let's go into this idea of resonance again. What is it? And a little bit more about why we're concerned about it. The easiest way to answer that question is to define resonance in terms of a single degree of freedom spring mass system, the so-called SDOF, single degree of freedom. And what we're interested in is natural frequency and resonance, sometimes with these fundamentals, well, and then certainly with harmonics. So here's our single degree of freedom spring mass system. So we have a mass here supported on some spring to a foundation, which is infinitely greater than the mass that we're shaking. And it's all done through some damping device. And the damping simply means that once excited, this system will eventually decay to zero in terms of its response. Okay? So if we put a response accelerometer on the top and started this thing exciting, what we would see is this the response input ratio. So this is the response, inputs measured someplace here, and at low frequency, the ratio between those two is 1. Input and response are identical. As we continue to increase the frequency, we'll get to some point where the response is very much higher than the input here. And then if we continue to increase the frequency, the response decays and eventually becomes very much less than the input. That's the kind of the classic resonant plot. We know that this natural frequency can be calculated just by the spring rate. In other words, the stiffness of the spring right here, so-called K value, and the mass. So if we know those two and we take the square root of them and multiply it by 1 over 2 pi, then we'll get this natural frequency. If you take the mass and put some gravity information into it, you wind up with a simplified version of 3.13 of the times the square root of the spring rate divided by the weight of this system. And that further simplifies into 3.13 times 1 over the difference between where this mass exists before and after the spring load is applied. Relatively easy to do. Okay, so resonance occurs when this system is forced to oscillate with the base being moved. So if you apply the force at the base here and you measure this response, then this plot here winds up being the natural frequency or resonance plot. If in fact you force the mass to move itself without moving the foundation, if you will, then we wind up with what's called the fundamental or the natural frequency of the system. That's where it wants to move, and the resonance occurs when this forcing frequency equals the natural frequency of the system. That's when resonance occurs. The classic case of resonance, you've probably heard of this, is when you take a system that's relatively fragile, or where the damping, this quantity is very low, and you excite it, and you can do that acoustically or manually or anything else. For the classic case of the wine glass, the soprano sings the same note where this glass likes to ring if you would tap it with your finger. And if you do that correctly, you can actually break the glass, and you've probably seen examples of that. So that's simply an example of exciting the natural frequency of that spring mass system at its resonance. So with that as a kind of a very brief and hopefully somewhat enlightening background, let's look at a couple of examples. Okay, and this example number 1 is where we have this spectrum. Spectrum is the response input ratio, the amplitude basically, as a function of frequency. So this might be typical data from a test laboratory. And what we see here is that there are 2 peaks identified. One is here at about 14 hertz and one's about 8 hertz. And there are some peaks that are identified there, and here's the data. So the question that we're going to ask is, what does this mean? What can you tell from this particular piece of data? This is the frequency domain, so this is not where we live, and therefore, what in the world is going on here? Well, let's take a look at this. So in this particular slide, we have a shrunk version of that frequency domain spectrum. And let's look at what we know. Well, we know our primary resonance is 14 hertz. So that's this point right here, and that's the peak. So we know at 14 hertz that this particular system responds at an amplitude of 14 times the input. So that if this is the so-called 0 line, and we go up to something above 10 to 1. So every time that this system feels 14 hertz, it multiplies it by an amplitude of 14 times. Okay, and we also know that there is a secondary resonance here of 8 at 8 hertz, and that the amplitude response is about 9 times the input. And we also know that beyond this one-to-one line here in this region, that the system attenuates vibration. In other words, there's no harmonics that are significant in this area. Okay, if that's what we know about it, are there any potential problems with this system? And there are some. We see that both the primary and the secondary resonance, so these 2 points, primary and secondary, okay, are in what we refer to as the dense transportation zone or envelope, which is about 4 to 16 hertz. What does that mean? Well, that means that if you put this system, whatever it represents, on a truck and start it down the road, it's going to get very high levels of input between 4 and 16 hertz. Why is that? Well, we know that a truck tire has a circumference of somewhere in the neighborhood of 35 to 40 inches. So if you take your ruler and look around it, that's about what you're going to get. So if you assume that that truck is going down the road at 55 to 60 miles an hour, we can ask the question, how many times does that truck tire turn over per second? Okay, well, it turns out that's going to be somewhere in the neighborhood of about 5 times per second. So about 5 hertz, if you will. So if it had a single off balance, every time it rolled around, it would be a bump, if you will, or some peak value here. And since truck tires rarely have a single off balance, they're going to have multiple off balances, and there's going to be multiple tires in the truck. So the lowest you're going to get is in the 4 to 5 hertz range, and you're going to go up to somewhere in the 4 times that or so to about 16 hertz before things start tailing off. So that's one of the reasons that we say that this particular band winds up being this so-called bands of this dense transportation input. That's why it occurs. And all the measurements that we've done of trucks tend to validate that. We know that this particular system from which this spectrum was drawn was a crated assembly on a cushioned pallet. So what does that mean? That means there's a mass on top of a spring. And so we can assume that one of these peaks, this one or this one, was the result of the pallet, in other words, the package resonance, and the other was the product structural resonance. Okay. Now we know from good package design work, and some of our previous webinars have talked about this as well, that there should be a 1 octave difference, a separation between these two. In other words, the difference between 8 and 14 hertz should be 1 octave. What does that mean? Well, it should be that an octave is a doubling of the frequency, so that the lowest package resonance should be half of the product resonance here. So we know that these two are interfering with one another constructively because we don't have this 1 octave difference. Okay. So what's the result of that? Well, if this system that we're looking at here were on a truck, we know that this packaged product will likely have an average acceleration input on that truck of perhaps a quarter of a G RMS. So that's about what we can expect from a truck vehicle just going down the road over this frequency band of 8 to 14 hertz that we're interested in. So what it says is the package, which is likely this lower frequency, this 8 hertz, will increase or multiply the input by a factor of 9. That's what this 9x is all about. So every time it experiences input in the region of 8 hertz, it multiplies that input by a factor of 9. Okay, so this 0.2 G RMS input is now 2.25 G, or 9 times 0.25 through the package and into the product. So, and then the product takes this input from the package, which is now 2.25 Gs at 14 hertz, because that's where it resonates, and it multiplies it by a factor of 12. Okay, resulting in because that's the peak amplitude of the product response there, and it results in a net of basically 14 times 2.25, or 27 Gs. 14 times a second, 14 hertz. Okay, so as this product package system is put on a truck and going down the road, and it could just a normal road, normal truck, it's going to get 27 Gs 14 times a second at at that uh, at that natural frequency, 14 hertz. Okay, so what's likely to happen? Well, it's gonna likely have some real severe problems. Um, so what we can learn from this is that we're likely to have a damaged product once we get to the client, just based on the fact that these two inputs are very high and that they're in the frequency band of the dense region from distribution. Okay, so that much we can learn just by looking at that spectrum in the frequency domain. Here's another example. This one shows a spectrum. Again, has 3 peaks on it. This one and over this particular frequency band, again, amplitude versus frequency. So let's see what we can say about this particular frequency domain spectrum. What do we know about what we see there? Well, we see 3 frequencies: 16, 24, and 49 hertz. Okay, and the amplitude levels vary from 12x here at 16 hertz to 4 at both 24 and 49 hertz. Okay, so the potential problems we have here are is that the primary resonance, the primary amplification being 12 hertz, that's 12 times at 16 hertz, it may result in fatigue. You're going to get the chances are pretty good you're going to get some fatigue-related issues for mechanical systems. Another interesting thing is that the harmonics, which are the multiples of the fundamental here, are relatively high levels, and that the damping is minimal and the vibration attenuation doesn't occur until well after 60 hertz. So let me explain what that's all about. The harmonics there, when you have a relationship of 16, 24, and essentially 48 or 49 hertz, it's likely that the 48 or 49 hertz frequency is a harmonic. It's probably the third harmonic, or 3 times the primary resonance. Okay. The fact that you have a secondary resonance at 24 hertz may or may not be related to the fundamental at 16 hertz, but it certainly adds to the harmonic at 48 hertz, because 2 times 24 is going to be 48. So the chances are pretty good that this harmonic at 48 or 49 hertz is a result of some combination of the two fundamentals at lower frequency. Okay, so right away that raises some red flags. This is probably going to have some serious consequences, and those consequences are likely some high level of scuffing, and scuffing results from fatigue of components that are closely related to one another, so they're basically scraping across one another, and then fatigue damage to sensitive components. So in a case like that, where you have virtually no attenuation below 60 hertz, the chances are pretty good that vibration-related damage is going to be on your horizon. So again, we can tell that just by looking at this very simple input here, this is a spectrum, and saying, hey, this thing that has some characteristics that we just don't like. Here's a third example. This one is relatively simple. We see again, the amplitude versus frequency spectrum characteristics. This has a single peak here of 12 hertz at an amplitude level of about 5 times the input. Okay, and then a pretty quick decay of that response thereafter. Okay, so again, what can we say about this? Well, this is an entirely different story than the first two. With a primary resonance of 12 hertz with an amplitude of 5 times the input, we see no significant secondary resonances or harmonics. Basically, after we reach our natural frequency peak, things decay pretty rapidly after that. And by this decay, I mean that the response input ratio is less than 1, which means that we are attenuating vibration input, likely with a package system. So are there any potential problems with this? And my analysis is none. We see good damping characteristics, which means that this peak is relatively low and it decays rapidly after the peak is reached. We see a reasonable natural frequency for a package system here of about 12 hertz. So in this particular case, I'm very confident predicting successful shipment of this particular system. And again, I don't know what it looks like. All I know is its response characteristics and what's likely to occur during distribution. And from those two, I can tell you that's likely to be a good shipment. Now, I mentioned what the term damping, and I do want to make sure that you understand what that is, at least in a general characteristic. So here we have a spectrum, again, a frequency versus amplitude plot. Both of these are normalized, which means they're divided by the input. So on the horizontal axis, we have the frequency response over input ratio. So when the response or input are identical, we have a ratio of 1 to 1, and so on. And then on the vertical axis, we have the amplitude response, or the amplitude of the input. And again, it's normalized. So what it tells us is that when we have a damping ratio, this R sub C equal to 1, that the system doesn't amplify at all at its natural frequency, and it returns to a relatively benign or 1 to 1 ratio here as soon as the excitation is removed. As the damping ratio gets less and less, we see that there's an amplification this level, and at one of the lower, what I'm going to call less desirable damping coefficients, R sub C of 0.005, we see that the amplitude of the response can be in the neighborhood of 10 to 50 times the input. And that's in what we call the so-called dangerous area. So a well-damped system is going to have a relatively low level of response in this area, and ideally at 1, but we almost never see that. A poorly damped system is going to have a fairly high response here, and by poorly damped I mean this damping ratio of a very, very low level. And I've seen damping ratios here over 100 to 1. And what that simply means is that there's virtually no damping. And from a package standpoint, what we're trying to show here is a package natural frequency with a component within the product here above it. And they form the so-called complex spring mass system. And this Q, which is the amplification level, can get to be 100 or more relatively easily with these low damping coefficients. So we have to avoid those things. It's fairly easy to do, and we talked a little bit about the damping ratio of cushion systems in other webinars. It's something to be aware of if you have a complex system and are concerned about damage or fatigue during shipment. Another thing to be concerned about when you review these frequency domain spectra is the fact that most of the time the actual systems are multiple degree of freedoms, MDOFs. And some of what I've shown you, the samples are actually single degree of freedom systems. But that when you have a multiple degree of freedom, and this is this is our version of what that might look like in terms of a model. It could be that one system is oscillating or resonating at the same frequency that another one is, creating what's referred to as a constructive interference. Other systems might be resonating at frequencies that are so-called odd harmonics, where you have a destructive interference between the two systems. The only reason I'm showing this is not to confuse people, but just to say that sometimes the characteristics of the system that you're trying to diagnose can be quite complex. And a lot of times it's because of so-called constructive and destructive interferences of the spring mass systems that comprise this multiple degree of freedom spring mass system. So sometimes they're not as simple as I've made them out to be during this very brief excursion into the frequency domain. Sometimes they're quite complex, And a lot of that complexity has to do with the fact that there are multiple degree of freedom systems. It's also important to recognize that these MDOFs, or multiple systems, are the real world. Okay, that's really what we have to deal with, and that they're much more complex than the single degree of freedom system, and you know that. We simply use these SDOF, these single degree of freedom systems, because they're simple to understand, and they make our life much easier. But that doesn't mean it's the real world. The real world is really these so-called multiple degree of freedom systems, and your life is a whole lot more complex when you're actually dealing in that area. Let's move on to a case study that shows this quite well. This was a large frame product that was ripe for error in distribution, and it's as a cushion during shipment. It's put on a what's referred to as a floating deck system. So that basically is adhered to a wooden base that is glued onto these cushions down here. And this whole system is put onto a vibration machine in order to do the analysis that we're talking about. So that's kind of the model here. And we're actually monitoring on a very flexible component. It was part of the control box on this particular system. And so this was the background of the system that we're going to use for this particular case study. So when we did the product itself, we call it the bare product resonance search test. So in this particular test, we're asking the product, where do you resonate? In other words, where are your natural frequencies, product? There's no package involved in this thing at all. So what we found here was that the bare product resonated at 8 hertz. Right here. Again, this is amplitude versus frequency. And that at 8 hertz, it had an amplification level of about 23 times the input. So if we were giving this thing an input of like a 0.25 G RMS, it responded at a level of 25 or 23 times that at 8 hertz. So this thing is very poorly damped, that much you can say. Okay. So that's simply a product characteristic. It's not good or bad. That's simply what the product is. So we took that product then, and we obviously monitored a whole bunch of other areas, but this was the one of concern. When we took that same product and put it on its package system, guess what we found? the package transmitted a response at also at 8 hertz. Okay, and the combination of the product and the package at 8 hertz wound up being 55 times the input. Amazing. So there's virtually no damping at all in this thing. So what does this mean, 55 times the input? That means that when this product package system is placed on a truck and it goes down the road, if you will, that it's going to get a fairly high level of this 8 hertz, because that's right in the frequency band of concern, the 4 to 16 hertz. And that every time it feels that, it responds at a level of 55 times the input. That's an amazing number. So what can we say about that? Well, again, a review of what we know. The product and package both resonated at 8 hertz. 8 hertz is in the center of this so-called dense transportation envelope band from 4 to 16 hertz. And both product and package are lightly damped. So the potential problems here are fatigue damage, lots of it, excessive scuffing, and I would say lots of that, probably a lot of loosening of fasteners. So this thing is basically going to shake itself to death moving down the road. That can pretty much predict. So the conclusion we can draw from that is that this product has virtually no chance of surviving transportation. Every time it reaches 8 hertz, which is going to happen a lot, it's going to respond at 55 times the input, and that's going to be very high acceleration levels. So this is what I call perhaps an unshippable product in its current format. Is it unshippable? Well, maybe not, but you certainly have to remove that particular component and pack it separately for shipment. Otherwise, it's going to get destroyed. This is an example of what I call a package that will actually destroy the product. The package is supposed to protect the product. In this particular case, it will actually destroy it. So this winds up being an example that we really want to be able to have everyone recognize that in this particular frequency domain analysis, that here is something that you want to avoid. Again, you may or may not experience this yourself, but the product certainly will. Okay, I've done a lot of talking here, so I'm gonna ask Edmund if he can fill us in on any questions that you may have that I might be able to address as part of this webinar. Edmund?
Absolutely, Herb. So looking at the questions list, I'll just start from the top. First one is, are there standard vibration tests for packaging?
Well, there certainly are. I should comment that you don't really need a so-called standard vibration test to determine the vibration performance of a package system. All you need to do is excite it. So all you're looking for is the response input ratio and the frequency at resonance. And you can do that with almost any kind of the vibration input, or actually acoustical input too. You just have to excite the product and package system. But there are standard test procedures. ASTM D4728 is a classic one for some vibration performance. Or if you're looking to reproduce the distribution environment in the laboratory, there's the ASTM 4728, 4169, and 7386 are typical standards. Edmund, any other questions?
Yes, there are. Second question is, what random vibration inputs or profiles are used to find resonance?
Oh, good question, and closely related to the first question. And you don't really need any particular standard, but if you prefer to use them, then the ones previously mentioned work really well. ASTM D4728, ASTM D999 is an older version, kind of long in the tooth, but still useful. There are ISTA spectra that are recommended to reproduce the distribution environment in the laboratory, and they will work as well. They're intended for what's referred to as package integrity, which I define as the ability to withstand the distribution environment if you don't know resonance. But they work equally well for actually finding resonance in product or package systems in the laboratory. There's some ISO standards that do the same thing. I'm not familiar with the exact numbers, but there are plenty of standards that will do for this. But I also want to emphasize that you don't really need them. You don't really need a standard. All you have to do is excite the product package system. Okay, Edmund, what's next on our list?
Next on the list is, what is the best practice or method for determining locations of accelerometers?
Oh, there's a good one. Someone was paying attention. That's good. A good question. And the question is basically, where do I monitor the product or package system? And in general, what we're looking for is the lowest natural frequency of the product. That's the holy grail, if you will. And the reason is that if you protect for the lowest frequency, then the higher frequencies are normally protected as well. It depends on the design, but normally that's the case. So you're looking for lower frequency elements within the product, and these lower frequency elements, and let me define that. That's basically something that resonates at a lower frequency. That means that higher displacements, the lower the frequency, the higher displacement. So you can generally tell where to monitor by simply looking for things that move, things that when you push on them actually respond, they deflect. And that's almost always what I do, looking for places to monitor. I look for the most flexible components and always measure there. And that's not always the case, but there might be critical elements at higher frequencies and lower displacements, and therefore they're stiffer. But you can almost always tell those by running a test and seeing which ones fail, things like that. But almost always I just poke around and look for the most flexible elements. Okay, Edmund, any other questions?
Yes, sir. Last one for today. So his question is, what is the dense frequency band for truck and air? What frequencies should you pretty much be wary of?
Oh, another excellent question. Um, we have truck frequencies are the 4 to 16 hertz that I mentioned earlier, and that comes about because of the suspension of the vehicle, the wheels, and the springs. A lot of those times they're air springs. A lot of people ask, is there a big difference in the input between air ride suspension on a vehicle and leaf spring or other kind of suspensions on trucks? And the answer is, yeah, there is a big difference, but it's almost always in the amplitude, not necessarily in the frequency bandwidth, if you will. But the amplitude is decreased with airbags. So for trucks, 4 to 16 hertz is pretty common. Aircraft, much higher frequency. These are turbine, almost always, devices, and they're up in the hundreds of hertz range, but the amplitudes are much, much lower. So oftentimes they're not of major interest to us because they, for example, what does it take to dampen out 100 hertz? Well, a piece of paper is a pretty good damping medium for that, because the actual amplitude necessary to generate 1G at 100 hertz winds up being like 6 thousandths of an inch, something like that. And a piece of paper is typically 12 to 15,000, so it's going to dampen out that kind of stuff pretty easily. So aircraft, certainly in the 100 to 200 range, but normally not of concern for most products. Not all, but most. In the morning webinar, someone said, hey, what if I'm putting instrumentation on an aircraft? What frequency should I worry about then? Well, then you got to worry about the high frequencies, 100 to 200 hertz in that range. And so those are going to be important. But for distribution, for normal shipment, for bodies, for almost anything on an aircraft other than those that are bolted to it, then the lower frequencies are almost always of greater concern to you. Okay. Edmund, are there any more that stuck in under the wire there?
Yes, actually, there's one last question that snuck in just in this last minute. It's, how do you ensure your accelerometers don't affect the resonance of the object under test? For example, a light circuit board without standoffs in the center.
Excellent question. Remember that we're testing a spring mass system here, and if your product is so light that the mass of the accelerometer significantly adds to that mass, then you're going to change the results. So you got to be real careful about that. The general rule is that was explained to me years ago, and different people have different general rules, is that if the mass of the transducer, in this case an accelerometer, is 1/50th the mass of the product, then you're going to start changing things. And that was simply one person's, he's a very knowledgeable person, but that's just one person's guideline. And so anytime that the mass of the transducer significantly changes the mass of the product, then you're going to change its resonance as you measure it. So what do you do if you can't, if the mass of the product is so light? We actually tested products that were in essence the same mass as your eardrum. Well, that's in the microgram range, so how in the world do you measure that? You sure as heck don't glue a transducer to it. But what you can do is use a non-contact device, such as a laser vibrometer, where it doesn't actually attach to the product that you're measuring, but you can in fact determine its deflection through the use of a laser. So there's a bunch of different techniques, but it's a very good question, very astute, and I appreciate whoever sent that in for doing that, because you really have to be careful about that process. And we have run into trouble where we've actually put a transducer in a product and changed its natural frequency just because of the mass of the transducer. Most of the time, that's not a big concern, but if it is, there are other techniques available. Okay, Edmund, I'm going to turn it back over to you. And as I do, I want to say thank you to everyone who attended. And again, if you have any questions that occur to you, please submit them in the format, and please fill out the evaluation that Edmund will tell you about. And it's been my pleasure talking to you today. So, Edmund, back to you.
Thank you, Herb, and thank you for the fine presentation and the very insightful answers. That being said, if you missed anything or would like to listen to this webinar again, please go to WESTPAK's website at www.westpak.com under the Resources and Webinars tab. The webinar's material should also be uploaded by Friday. Our next webinar is entitled Sample Size Rationale for Medical Device Package Validation and planned for December 13th. We hope you can join us for this special presentation. Please check our website under the Resources and Webinars tabs for more information later on. You can register from there or wait for a personal invitation to arrive in your inbox. Lastly, we'll be sending you a short survey within the hour. Please fill it out as we highly value your opinion regarding today's webinar. You'll also have an opportunity to ask more questions or suggest a new topic for a webinar in the future. We have 2 locations, one in San Jose, California, and the other in San Diego, California. Please contact us directly with any test questions, information, or simply a quote for testing. Thank you all for attending. My name is Edmund Tang, and everyone have a great day.